A quiet visitor from between the stars, the interstellar wanderers. They drift through the dark, unanchored by any single sun, moving silently through the immense gulf between galaxies. These travelers are remnants and messengers, carrying dust, ice, and secrets from systems we may never know. They enter our solar system rarely, like whispers through an open window. Each one carries with it the marks of ancient stars long gone, the signatures of alien chemistry, and the mystery of where it began. The space between the stars is vast and cold, but even there, the universe sends small reminders that we are not alone in its motion. When the first of these wanderers came to our attention, a slender, tumbling shape called Oumuamua, it startled astronomers. It was unlike any asteroid or comet we had ever seen. It spun end over end, reflecting sunlight in strange patterns. No gases trailed behind it, no dust cloud betrayed its composition. It was as though it were made of something hardened by cosmic ages, something forged far beyond our reach. For a brief moment, humanity's telescopes followed it as it swept around the sun, curving gracefully before vanishing back into interstellar night. Another followed years later, Borisov, more familiar in its behavior, a comet shedding vapor and ice, glowing softly as it neared our sun. Yet it too had come from beyond, moving faster than any native body of our solar system. It was proof that Oumuamua had not been an anomaly. The galaxy, it seemed, was full of drifting debris, fragments of planets and comets ejected from their home stars. Every solar system, when young and restless, throws some of its children away, sending them into the dark to wander for eternity. These travelers are like cosmic messages written in matter. They cross light years, carrying within them frozen molecules and metallic grains that tell of the environments they were born in. By studying their motion, their light, and their chemistry, we glimpse what other planetary systems might be like, what temperatures their suns shine with, what elements fill their skies. Each interstellar object is a fragment of a forgotten story, carried forward in silence, unknowing of the civilizations that will one day notice it and wonder. Imagine them drifting through space, untouched for millions of years. Passing the glow of distant stars, slipping through thin tendrils of gas, listening to nothing but the cosmic background's soft hum. They do not age in the way we understand. The cold preserves them, the void keeps them pure. Some may have left their systems during violent events, collisions, gravitational slingshots, or the deaths of their suns. Others might have escaped gently, tugged free by the slow dance of other planets. But once gone, they become eternal drifters, unclaimed and unseen until chance brings them near another star. The distances they travel are unimaginable. Between stars lie light-years of emptiness, so wide that even light, the fastest traveler of all, takes ages to cross them. And yet, these wanderers make that journey without fuel, without purpose. Their momentum, once set, is endless. A small push from their birthplace is all it takes to set them adrift forever. They move along quiet, unchanging paths, obeying nothing but gravity's subtle pull and the occasional whisper of a starlight's pressure. When one enters our solar system, it carries the chill of that long journey. Its surface, baked by radiation, may glisten faintly, its outer layers scarred by the cosmic wind. As it approaches our sun, heat begins to awaken it. Ice turns to vapor, dust begins to rise, and a faint tail may emerge. To us, it is a spectacle. To the wanderer, it is a momentary warmth before the cold returns. It will soon leave again, slipping back into the darkness, leaving behind a faint trace of its presence in our memory and our data. Astronomers watch these visitors closely because they hold clues about what lies beyond our solar boundaries. They are natural probes, fragments of alien systems delivered to us for study. Each one offers a new chance to test our understanding of how stars form, how planets scatter, and how materials evolve in the interstellar medium. A piece of dust from one of these travelers might reveal molecules never seen before, hinting at chemistry that unfolds differently elsewhere in the galaxy. Some even wonder if interstellar wanderers could be carriers of life's raw ingredients. Amino acids, carbon chains, and frozen water all could survive the vast journey through space. If these materials were to land upon a planet like ours, they might seed new beginnings. In that way, these drifters could be part of a grand cosmic cycle, spreading the basic ingredients of biology from one world to another. They may be lifeless stones, But in their silence, they carry the potential for life's spark to travel between stars. Our telescopes, though powerful, only see them briefly. By the time we detect one, it is already racing away. They arrive unannounced and depart swiftly, leaving us only with measurements, images, and imagination. Future generations may send probes to intercept them, to sample their material and read their history directly. For now, we only dream, but that dream grows stronger with every sighting, every detection that whispers, another visitor has come. The thought that countless others drift unseen between the stars is humbling. Most will never cross paths with any solar system. They will wander in solitude, cold and eternal, their only companion the faint glow of distant galaxies. But every so often, one finds a way into a star's domain, like a leaf caught by a gentle eddy in a vast, invisible sea. For a few fleeting years, it joins our cosmic story before slipping away again. Their origins are chaotic. In young solar systems, where planets are still forming, gravitational battles rage. Some asteroids are hurled inward toward the parent star, others flung outward at escape velocity. Those that reach the edge of their system may find themselves free, released into the galactic stream. There, they drift endlessly, pulled slightly by the gravity of passing stars, until chance brings them near a new home. Each one is a relic of a creation long past, a record of the early days of some forgotten sun. Over time, their surfaces change. Radiation darkens them, impacts reshape them, cosmic rays etch them with invisible scars. They become timeless artifacts, carrying within their cores the pristine chemistry of their birthplaces. To study one closely would be like touching the oldest part of the galaxy's history, a piece that has seen countless epochs and crossed through the invisible threads that bind the Milky Way together. Some imagine that within their rocky hearts might lie traces of alien worlds, the minerals of long-lost planets, perhaps even microscopic fossils if life ever arose elsewhere. It is an extraordinary thought, that a single stone could travel between stars, holding within it the memory of another world. Though such ideas remain speculation, they remind us of how deeply connected the universe could be, how even the most distant systems might share a link through drifting messengers of stone and ice. As our technology improves, we may begin to detect these visitors more often. Sensitive instruments now scan the sky each night, searching for small, fast-moving points of light. The moment one is spotted, scientists rush to gather data before it vanishes again. Every new discovery reshapes our understanding of the galaxy's hidden traffic, a quiet network of objects passing silently from one star to another, unseen for eons until light catches them for a brief instant. Perhaps one day we will send a craft to chase such a visitor, a silent rendezvous in the dark between stars. The probe could study its surface, its chemistry, and its internal structure. It would be like touching another world without ever leaving our own star's reach. We could learn how other systems form their comets, what elements fill their planets, and perhaps even whether life's potential ingredients are scattered everywhere. These thoughts remind us how small we are, and yet how deeply connected we might be to the wider cosmos. Every interstellar traveler is a thread linking one star's story to another. We, too, are made of interstellar material atoms forged in old stars, scattered by explosions, and gathered into our world. In a way, we are wanderers ourselves, born of cosmic debris and destined to return to it one day. When you imagine one of these objects gliding silently past our world, think of the immense distances it has crossed. Think of the forgotten suns that once warmed it, the collisions that might have set it free. It has seen no light but starlight, felt no touch but gravity, heard no sound but the whisper of cosmic dust. And now, for a moment, it brushes close to our sun, a fleeting intersection of paths in the endless darkness. The stars themselves may barely notice. The universe carries on in its slow rhythm. Yet, for us, these brief visits awaken something profound, a reminder of the vast, shared ocean we drift in. Space is not empty, it is alive with travelers, each one a story written across time and distance. To find them is to listen to the quiet language of the galaxy. When the visitor departs, it leaves behind more than data. It leaves wonder, the sense that something ancient and immense has passed close to us, unnoticed by all but a few patient eyes. We watch it fade into the dark, shrinking until it becomes a point of nothing. But even as it disappears, its journey continues, endless and serene, guided only by the unseen pull of the stars. And so, the interstellar wanderers go on, slipping between systems, unbothered by ages or destinies. They are the quiet nomads of the galaxy, timeless and alone, carrying fragments of everything that has ever been. In their silence, there is comfort, a slow, cosmic rhythm that reminds us of continuity, of movement, of the unending conversation between stars. When we close our eyes, we can almost feel them passing by, slow and steady, somewhere far beyond the night. Rogue planets, lonely worlds adrift in blackness. They roam the galaxy without a sun to guide them, without the warmth of any star to light their skies. They drift through eternal night, their paths uncertain, their surfaces cold beyond measure. These are planets without homes, torn away from their parent stars long ago, set loose into the silent sea between systems. Each one is a world complete unto itself, carrying mountains, oceans, and atmospheres that now sleep under endless darkness. Some wander close to starlight from time to time, but most are swallowed by the invisible, traveling alone through a universe that has forgotten their names. The birth of a rogue planet often begins in chaos. Young solar systems are turbulent places, filled with collisions and gravitational struggles. In those early ages, worlds pull at one another like dancers in a crowded hall. Some grow, some fall, and some are flung away. A close encounter with a giant planet or a passing star can send a smaller world hurtling into the void. It is a violent exile, one instant, a warm sunrise, the next, a permanent night. Yet even cast away, these planets endure, carrying the silent echo of the systems that once gave them life. Imagine such a planet, drifting endlessly in the dark. The only light comes from distant stars, faint as pinpricks on an ink-black sky. There is no day, no season, no sunrise to mark the passing of time. If it once had an atmosphere, it may now be frozen solid, a shell of still air encasing a sleeping core. If it had oceans, they may be locked in ice, stretching silent and unmoving over its surface. And deep beneath that frozen layer, warmth might still linger, the fading breath of a planet's heart, holding on to heat long after its sun has gone. Some rogue planets might still be warm inside. Radioactive elements and the slow compression of their cores can keep their interiors alive. Beneath miles of ice, liquid oceans could remain, hidden and untouched. In that secret warmth, simple forms of life might endure, microbes feeding on chemical energy, adapting to eternal night. It is a haunting thought, that somewhere in the dark between stars, unseen and unreachable, entire worlds could be quietly alive, lit only by the glow of their own inner fire. Others are colder still, frozen solid from crust to core. Their mountains crack from the strain of the cold, their valleys filled with shadow. If you stood upon one, the silence would be beyond measure. You would see nothing but darkness, interrupted only by faraway stars, each one a sun that will never rise for you. There would be no wind, no birds, no clouds. Only the faint whisper of your own breath against the endless night. A rogue planet is not merely cold, it is solitude made into stone. Scientists believe there may be billions of these lonely worlds drifting through the Milky Way. Some may be as small as the Moon, others as massive as Jupiter. They are everywhere, scattered like forgotten marbles across the galactic floor. Each one has its own story, a violent beginning, a lost orbit, a slow descent into the unknown. They are the orphans of the cosmos, wandering between stars that will never notice them, following paths that lead nowhere. And yet, they move with quiet grace, obeying only the laws of gravity, patient as time itself. For astronomers, these planets are difficult to find. Without a nearby star to reflect light, they remain nearly invisible. Sometimes, their presence is betrayed when they pass in front of a distant star, briefly bending its light, a phenomenon called gravitational microlensing. In those brief moments, we catch a shadow, a curve of light, a hint of a hidden world. And then it is gone again, swallowed by darkness, leaving behind only a trace in our instruments and an ache of curiosity in our hearts. Some theories suggest that these worlds might once have hosted life. Imagine a thriving planet orbiting a warm sun, covered in oceans and forests. Then, a catastrophic encounter, another planet's gravity pulling it loose, sending it spiraling into the void. The seas freeze, the atmosphere collapses, and life retreats into deep caverns where heat still flows. Over time, that life might evolve, adapting to the darkness, feeding on minerals and heat. Such a world would be invisible to us, but alive in ways we cannot imagine. There are even rogue planets that glow faintly from within. Young, massive ones retain the heat of their birth for millions of years, radiating warmth into the blackness. They drift like dim embers in the night, glowing in infrared light, heat without a flame, presence without illumination. For any traveler of the cosmos, such a planet would appear like a lonely lantern in the dark, moving slowly through the silent sea of stars. In the future, we may learn to find them more easily. Sensitive infrared telescopes will one day map the faint heat signatures of these hidden wanderers. Each discovery will tell us something new about how planets form and how they die. We may even send probes someday, small, patient machines that drift for centuries through interstellar space until they find one of these lost worlds. To land on a rogue planet would be to stand upon solitude itself, to touch the cold bones of creation. The most haunting part of rogue planets is their silence. There is no sound in space, but on these worlds, even within an atmosphere, silence would feel different, deeper, heavier. No rustle of trees, no rush of waves, no echo of life. Just the steady stillness of stone and ice. It is a silence that speaks of the universe's vast indifference, yet within that stillness lies a strange peace, the calm of something eternal, untouched, and unbroken. In the depths of imagination, one can picture civilizations that once lived on these planets before their exile. Perhaps they saw their sun grow distant and dim, their days stretching into years, until finally, it was gone. Perhaps they built shelters deep underground, powered by the planet's heat, clinging to survival in the eternal night. If any such beings still exist, they would live under skies where the stars never move, a frozen eternity without dawn or dusk. But not all rogue planets are the victims of chaos. Some might have been born free, formed from gas and dust that never gathered around a star. These are true children of the void, created in isolation, never knowing sunlight at all. Their skies have always been dark, their landscapes unlit since the first moment of their creation. They are ancient, untouched, and unknowable, a reminder that not all life or existence requires a sun to begin. For us, the idea of such a world feels both terrifying and serene. We imagine ourselves standing upon it, our own breath fogging in the cold, the universe stretching infinitely above. There would be no horizon, only darkness. The stars would seem close enough to touch, yet impossibly far. On such a world, time would lose meaning. Without a sun to rise or set, days and nights would blend into one endless now. Some scientists think that rogue planets might play a role in galactic evolution. As they drift, they may capture debris, dust, or even small moons. Over billions of years, they could sweep through dense regions of space, collecting material that later seeds new stars and systems. Even in their loneliness, they might contribute to the grand cycle, breaking down and building up the galaxy, silently helping creation continue. In fiction, rogue planets often become symbols of loss, of solitude, of endurance. They remind us of how fragile stability is, how easy it is to be cast away. Yet they also show resilience. A planet that survives without a sun endures the harshest fate imaginable, and still remains whole. Its core still beats faintly, its structure still holds. It drifts on, waiting for no one, needing nothing. If humanity ever travels between stars, we may find these worlds first. They could serve as waypoints in the dark, resting places between systems. A rogue planet with a thick atmosphere or internal heat could one day host explorers, offering a brief shelter in the cosmic wilderness. What was once a symbol of exile might become a beacon of endurance, a reminder that even in the void, something can persist. There may even be one closer than we think, perhaps drifting beyond the edges of our solar system, too faint to see, too dark to reflect sunlight. Some models suggest a large planet-sized body could be moving slowly through the outer regions, unnoticed. If so, it would be a rogue of sorts, not quite bound, not quite free. A quiet shadow, circling our sun at an immense distance, waiting for our gaze to find it. For now, we only imagine. Our instruments catch hints, our theories trace possibilities, But the rogue planets remain out there, indifferent to our curiosity. They move as they always have, unhurried, unseen, unbound. Each one carries the quiet dignity of an ancient traveler, untouched by the light that guides all others. When we close our eyes and think of them, we might feel something like empathy, a kinship with their endless journey. For we too drift, in our small blue world, circling one star among billions, moving through the darkness toward destinations unknown. Perhaps, in some distant age, even Earth might become a rogue planet, cast free after our sun's long death, carrying the memory of life into the black. And so the rogue planets continue their eternal voyage, solitary and steadfast. They ask for nothing, they expect nothing, yet they embody endurance itself. Each one glides through infinity, silent but not forgotten. They remind us that in the great quiet of the universe, even isolation can have its own kind of beauty, and that sometimes, even the loneliest worlds are part of something vast, endless, and serene. Supernovae, the bright, final shout of a dying star. They are the universe's grandest farewells, the instant when a star's long and steady life erupts into unimaginable brilliance. For millions of years, it burns quietly, fusing elements in its heart, balancing gravity's pull against its own energy. But that balance cannot last forever. When the fuel runs low, when the heart can no longer resist its own weight, collapse begins, sudden, unstoppable. In a heartbeat, the star implodes, then explodes, tearing itself apart in a flash so bright it can outshine an entire galaxy for a short, blinding time. Imagine the silence before it happens, a massive star, heavy and weary, glowing faintly red in its final age. Deep inside, its core is no longer a peaceful furnace but a layered forge, turning lighter elements into heavier ones, iron forming at the very center. Iron is the end, for it gives no more energy back. Once the core fills with it, the star's strength fails. In less than a second, gravity wins. The star's heart collapses inward, crushing atoms, shattering the boundaries between matter and energy. Then, as if the universe itself gasps, the outer layers rebound outward in a titanic blast. The explosion sends shockwaves racing through space at incredible speed. Temperatures soar beyond imagination, and the star's matter is ripped apart, hurled outward in a glowing shell of gas and plasma. For a few weeks or months, that dying star becomes one of the brightest objects in the night sky. Even from thousands of light-years away, its light can reach us, a final cry echoing across time, telling of creation and destruction bound together in a single event. Then slowly, the light fades, leaving behind silence and ashes drifting through the cosmos. But a supernova is not just an end, it is also a beginning. The tremendous heat and pressure of the explosion create new elements: gold, silver, uranium, and countless others that never existed before. These precious materials are scattered into space, becoming the raw ingredients for future stars, planets, and even life. Every atom of iron in our blood, every trace of gold in the Earth's crust, was once forged in the heart of a dying star. In that way, supernovae are the universe's great alchemists, turning death into renewal, chaos into creation. Sometimes, what remains after the blast is even stranger. The core that collapses may become a neutron star, a sphere so dense that a teaspoon of its matter weighs billions of tons. It spins rapidly, sending beams of radiation into space like a cosmic lighthouse. If the star was even more massive, it might collapse entirely into a black hole, a point where gravity becomes so strong that not even light can escape. From that moment on, the star's story continues invisibly, its presence felt only through its pull on the space around it. The light from a supernova travels far and endures long after the event itself is gone. Sometimes, ancient astronomers recorded sudden new stars appearing in the sky, bright enough to see in daylight, then fading slowly over months. They could not know that what they saw were stars dying in distant corners of the galaxy. Today, when we observe the faint remnants of those explosions, we are looking at the echoes of light that left their source centuries ago, traveling patiently through space to reach our waiting eyes. The debris from a supernova expands endlessly, creating vast clouds of glowing gas called nebulae. These clouds are beautiful, intricate swirls of color and light shaped by invisible winds and magnetic fields. Within them, new stars will one day form, born from the ashes of their ancestors. It is a perfect cycle. Stars are born, they shine, they die, and from their death, new stars rise. The universe is both destroyer and creator, endlessly renewing itself in waves of brilliance and silence. To witness a supernova in real time would be to see both terror and beauty combined. The flash begins small, then blossoms outward with overwhelming brightness. Space around it fills with radiation, shock, and energy beyond human scale. In that instant, the star's light carries information about its entire life, the composition of its elements, the rhythm of its final heartbeat. It is the universe's most powerful kind of memory, written not in words, but in light and energy. There are different kinds of supernovae, each with its own story. Some come from massive stars collapsing under their own weight. Others happen when a small, dense star steals too much material from a nearby companion, igniting runaway reactions that tear it apart. The details differ, but the result is always the same: a blinding burst, a fading afterglow, and a legacy that stretches across light years. Each type tells us something new about how stars live, how they die, and how galaxies change over time. When a supernova occurs nearby in astronomical terms, within a few hundred light-years, it can have profound effects. Its radiation can sweep across space, stripping atmospheres from planets, altering chemistry, even sparking new forms of evolution. Some scientists think ancient supernovae may have influenced Earth's own history, shaping the path of life by subtly changing the world's environment. In that way, the death of distant stars might have written small but crucial lines in our story too. The study of supernovae helps us measure the universe itself. Certain kinds, known as Type Ia supernovae, explode with almost the same brightness every time. Astronomers use them as cosmic yardsticks, measuring how far away galaxies are by comparing how bright they appear. Through them, we discovered that the universe's expansion is speeding up, driven by some mysterious force we call dark energy. Even in death, stars continue to teach us the secrets of existence. The aftermath of a supernova is both eerie and magnificent. In the center of the expanding cloud, the remnants of the star spin on a neutron star glowing with radiation, sometimes pulsing in perfect rhythm. Around it, dust and gas drift outward like the slow bloom of a cosmic flower. Over time, this material mixes with the interstellar medium, blending into the fabric of space until it becomes part of new stars, new planets, and new possibilities. Nothing is truly lost, it merely changes form. Some supernovae are so powerful that they reshape their entire galaxies. The shockwaves they release can compress nearby clouds of gas, triggering the birth of new stars. In this way, destruction gives rise to creation. The same event that ends one star's life may begin hundreds of others. This balance between ending and beginning is what gives the universe its rhythm, a constant dance of death and rebirth, silence and song. If you could stand safely at a distance and watch, the view would steal your breath. The sky would light up as though another sun had appeared. For days, it would glow with colors too bright for eyes to truly capture, whites and blues blending with gold, then fading into crimson and violet. The explosion would stretch across light years, its expanding shell glowing for thousands of years before finally dimming into the quiet dust of space. The elements we find here on Earth, carbon, calcium, oxygen, all come from ancient supernovae. Each breath you take, each heartbeat, carries atoms born in the fire of dying stars. When you look up at the night sky, you are not just seeing distant suns, you are seeing the same cosmic family that gave rise to everything you are. The stars die, but in their death, they leave behind the building blocks of all that lives and loves and dreams. In the distant universe, astronomers still witness these events every day. Their telescopes capture sudden bursts of light, the signatures of stars ending far beyond our galaxy. Some of those supernovae happened billions of years ago, their light is only reaching us now. Each one is a messenger from the past, a whisper from the deep time of the cosmos. To observe them is to look back across eternity, to see the universe remembering itself. Occasionally, a supernova will leave behind something extraordinary, a pulsar, spinning hundreds of times per second, emitting beams of energy like a ticking clock. Or a magnetar, whose magnetic field is so powerful that it can distort atoms. These remnants are reminders that even after destruction, there is structure, purpose, and strange beauty in what remains. The universe, it seems, never wastes its energy, it merely changes the way it shines. Supernovae also shape the galaxies we see. Their blasts stir the interstellar gas, enriching it with heavy elements, pushing and pulling it into new forms. Without them, galaxies would be dull, static things, clouds of hydrogen and helium drifting endlessly. It is through these explosions that galaxies breathe, mixing their matter, keeping their chemistry alive. The brilliance we see when we look up at the Milky Way owes its richness to countless ancient deaths. And yet, for all their violence, there is a gentleness in how they remind us of impermanence. Everything that burns bright must one day fade. The stars, for all their grandeur, follow this truth as we do. Their deaths are not tragic but natural, the closing of one chapter, the start of another. The light of a supernova is a cosmic exhale, a final release that seeds the universe with new potential. When the light finally fades, what remains is stillness, a dark void where once there was fire. But that silence is not empty. Within it lies the promise of future stars, of new worlds waiting to form. The ashes of the old become the soil of the new. The cycle continues quietly, endlessly, beyond our reach and comprehension. And so, the bright, final shout of a dying star becomes a lullaby. For creation. It tells of endings that give rise to beginnings, of light born from loss, of beauty that persists even in destruction. The universe listens, and the echoes ripple outward forever. Somewhere, even now, another star is reaching its final breath, preparing to illuminate the dark one last time before becoming part of everything again. In that light, fleeting and infinite, the cosmos remembers itself and rests. Neutron stars and pulsars, the densest remnants, spinning like tiny lighthouses. When a massive star ends its life in a supernova, the core that remains may compress so tightly that atoms themselves collapse. Protons and electrons fuse into neutrons, creating an object no larger than a city yet heavier than the sun. These strange remnants are called neutron stars, cosmic diamonds forged under unthinkable pressure. Their surfaces are smoother than glass, their gravity fierce enough to bend light, and their density beyond imagining. They are the quiet hearts left behind after stellar death, still beating with energy and rotation. Imagine a teaspoon of their matter, it would weigh billions of tons. Within that tiny fragment, the mass of mountains is crushed into the volume of a droplet. Gravity there is absolute, holding everything tightly together, allowing no weakness. The crust of a neutron star is a lattice of pure atomic nuclei, while beneath it, neutrons flow like a superfluid, a liquid that moves without resistance, friction, or sound. This is not matter as we know it, it is matter in its most extreme and purest state, stripped of all emptiness, squeezed to the edge of physics. Many neutron stars are not silent. They spin rapidly, sometimes hundreds of times per second, and their magnetic fields, trillions of times stronger than Earth's, twist and focus radiation into beams. As the star rotates, those beams sweep across space, flashing rhythmically toward distant observers. We call these spinning stars pulsars, because their light arrives in perfect, repeating pulses, like the ticking of a celestial clock. Each pulse is the heartbeat of a dead star, still alive in motion. The discovery of pulsars in the late 1960s was one of astronomy's great surprises. When the first signals were detected, steady, precise radio bursts coming from deep space, scientists briefly wondered if they had found signs of extraterrestrial intelligence. The signals were too regular, too deliberate. But soon it became clear, they were the echoes of rotating neutron stars, each one turning its light across the galaxy like a cosmic lighthouse. What seemed at first like communication was, in truth, the steady rhythm of nature's endurance. To picture a pulsar is to imagine something both terrifying and beautiful. A sphere only 20 kilometers wide, spinning faster than any machine, throwing out energy and radiation across space. Its magnetic field cracks and flickers, its surface glows with unimaginable heat. If you could somehow stand upon it, though no being could survive there, you would be crushed instantly, your atoms pulled apart, your sense of direction lost in a swirl of gravity so intense that time itself would slow. Yet, from a safe distance, its light seems calm, predictable, mesmerizing. Pulsars act as cosmic metronomes, their pulses so consistent that astronomers use them to measure time with incredible precision. The rotation of some pulsars is more stable than the ticking of atomic clocks. When their rhythm shifts even slightly, it tells us something. Perhaps the star has quaked, its crust cracking under immense stress, or perhaps it has absorbed matter from a companion. In their flickering patterns, pulsars reveal the deep mechanics of space and time, offering a glimpse into the fabric of reality itself. Sometimes neutron stars exist in pairs, orbiting one another in a furious dance. As they circle, their immense gravity distorts space, sending ripples outward, gravitational waves that we can now detect on Earth. These waves are the faint tremors of space-time itself, carrying news of distant cataclysms. When two neutron stars finally collide, the result is spectacular: a kilonova, brighter than a galaxy, scattering heavy elements like gold and platinum across the cosmos. From such collisions, much of the universe's most precious material is born. The life of a neutron star is long and patient. After its violent birth, it slowly cools, radiating away its heat over millions of years. Its spin, too, gradually slows, the once rapid pulses stretching farther apart until they fade into silence. What remains is a cold, dark ember drifting through space, a star's ghost, too dense to die but too still to shine. Even in that quiet state, it remains one of the strangest and most mysterious objects the universe has ever made. The structure of a neutron star defies human understanding. Beneath its thin outer crust lies a sea of neutrons so dense that quantum effects dominate every motion. The core may even hold exotic forms of matter, hyperions, quarks, or strange particles never observed elsewhere. It is a laboratory beyond reach, showing us what happens when nature pushes matter past its limits. Each neutron star is a cosmic experiment frozen in perfection, a question without a final answer. If a neutron star's magnetic field is especially powerful, it can become a magnetar, one of the most violent objects known. Magnetars occasionally release bursts of gamma rays and X-rays so intense they can be detected across galaxies. A single outburst can release more energy in 1 second than the sun emits in 100,000 years. Yet they are small, fragile-seeming things, only a few miles across, turning slowly in the dark. Their strength is unimaginable, but their lifetimes brief, fading after only a few tens of thousands of years. The radiation from pulsars travels far, whispering through the interstellar medium, reaching the antennas of telescopes on Earth. Each pulse arrives with perfect timing, sometimes separated by milliseconds, sometimes by seconds. Listening to them is like hearing the universe breathe, slow, steady, eternal. Their signals are so regular that they can be used to map our galaxy, to navigate spacecraft, and even to test Einstein's theory of relativity with exquisite precision. When two neutron stars orbit close together, they tug and twist at each other's gravity, distorting time around them. They spiral inward over millions of years, their dance tightening until they finally merge. The collision is unimaginably violent, a wave of energy, light, and new elements sweeping through space. From that chaos comes order, as new stars form from the debris, and the fabric of space-time itself ripples in silent waves. These are the cosmic symphonies we now listen for with our most sensitive instruments. Even a single neutron star can shape its surroundings. Its strong magnetic field can capture charged particles, creating glowing halos of radiation. If it drifts through a cloud of gas, it can pull the material toward itself, heating it until it shines in X-rays. Some of these stars have companions, and as they draw matter from them, they flare up again, briefly reborn as X-ray pulsars. The universe finds ways to awaken even the quietest remnants, stirring them back into light. The study of pulsars has become one of astronomy's great tools. They allow us to explore physics in extremes, gravity, magnetism, density, and time all operating at once. Through them, we learn not only about stars but about the very laws that govern existence. Each discovery deepens our awe, reminding us how far the universe can stretch the boundaries of what is possible. And yet, for all their complexity, pulsars remain astonishingly elegant: a simple rotation, a beam of light, a rhythm that never falters. Sometimes, when we detect their pulses, we are hearing signals that began their journey thousands of years ago. By the time their light reaches us, entire civilizations could have risen and fallen. Each pulse is a message from the past, a perfect echo of a moment long gone. The thought gives their sound a melancholy beauty, the rhythm of something that no longer exists, still speaking across the gulf of time. Neutron stars also remind us of the fragility of balance. They are the narrow boundary between existence and oblivion. If they were just a little heavier, they would collapse entirely into black holes, their identity lost forever. If they were lighter, they would remain ordinary stars or white dwarfs. They exist precisely at the edge, the last stop before the ultimate abyss. To look at them is to see nature balancing on a knife's edge, perfect and perilous at once. The crust of a neutron star may quake under its own tension, releasing bursts of energy that ripple through space. These starquakes can slightly alter the rotation, changing the timing of the pulses. It is strange to think that even such tiny movements, occurring hundreds of light-years away, can be measured here on Earth. In those tremors, we witness the nervous heartbeat of the densest matter known, a reminder that even dead stars are never truly still. If you could drift near a pulsar, its beams would sweep past you like slow flashes from a distant lighthouse, illuminating the dark with rhythm and grace. Each rotation would mark a passing moment, a reminder of cosmic time unfolding. The space around it would shimmer faintly with radiation, but beyond that glow, the universe would remain calm and vast, its silence broken only by the steady pulse of the star. Over billions of years, as the energy fades and the spin slows, the pulsar's light will dim and vanish. Yet it will continue to drift through space, carrying within it the history of its creation, the echo of the star that once burned, the memory of the explosion that set it free. Even when its beams no longer shine, the neutron star will persist, cold and silent, a relic of the universe's ancient fire. The thought of these tiny, dense remnants scattered throughout the galaxy is humbling. They are countless, each one the grave of a former giant, now reduced to a single spark of endurance. Some move through the galaxy at incredible speeds, hurled away by the force of their own birth. Others remain near their birthplace, hidden behind veils of gas. Together, they form a silent population unseen, but vital, holding within them the memory of stellar generations past. And so the neutron stars and pulsars continue their endless watch. Their light flickers through the darkness, slow and steady, marking time in a universe that often feels timeless. They are the keepers of cosmic rhythm, the survivors of unimaginable violence, and the storytellers of eternity. In their dense hearts lies the reminder that even after the brightest star dies, something endures, small, powerful, and full of memory. They are the universe's heartbeat, echoing softly through the night that never ends. Magnetars, magnetic monsters with invisible reach. These are neutron stars taken to their most extreme form, their magnetic fields 1,000 times stronger than even the fiercest pulsars. A magnetar's field is so powerful that it twists and strains the very fabric of its crust, cracking it like ice under pressure. If you stood near one, the magnetic force would tear apart your molecules, rearranging the atoms of your body as if they were nothing but mist. Yet from across light-years, their fury feels almost serene, quiet giants wrapped in unseen storms of invisible power. A magnetar is small, no larger than a city, yet within that sphere lies energy beyond comprehension. Its magnetic field is capable of distorting the shapes of atoms, forcing them into lines that point along its invisible flow. The star's surface crackles with energy, and sometimes that energy escapes in violent bursts of gamma rays and X-rays. These eruptions are so intense that they can outshine an entire galaxy for a few fleeting moments, a cosmic shout from something impossibly dense and unimaginably distant. The origin of a magnetar begins with death, the death of a massive star collapsing under its own gravity. When the star's core is crushed, the immense pressure gives birth to a neutron star. But if the conditions are just right, if the rotation is rapid and the internal currents strong, that newborn remnant becomes supercharged with magnetism. It spins, it seethes, and its magnetic field locks itself in place, freezing the power of an entire sun into a sphere of metal and fire. To understand how strong a magnetar's field is, imagine this: if one were placed halfway between the Earth and the Moon, it could wipe every credit card and erase every hard drive on Earth. Its field is so pervasive it can reach across space and pull at the electrons in matter, bending them to its will. Even light itself, under its influence, can be distorted, twisted and polarized in ways that challenge our deepest theories of physics. Magnetars are not merely stars, they are natural experiments in the very limits of electromagnetism. Sometimes, their surfaces become unstable. The crust, held in tension by the magnetic field, shifts and snaps in sudden, catastrophic quakes. These starquakes release bursts of radiation powerful enough to light up detectors across the galaxy. The energy unleashed in one of these events is greater than what the Sun emits in 100,000 years. Astronomers detect these as soft gamma repeaters, brief, recurring flares of unimaginable force, emerging from a single point in the sky. When the first magnetar burst was recorded, scientists were stunned. The pulse of gamma rays arrived suddenly, its intensity overwhelming instruments meant to study distant galaxies. It came from within our own Milky Way, a star that had gone quiet for centuries suddenly screaming across space. Since then, only a few dozen magnetars have been confirmed, though we believe there may be millions, hidden and sleeping, waiting for their next violent awakening. The surface of a magnetar glows faintly with residual heat, but beneath it lies chaos. The interior is a dense ocean of neutrons, mixed with currents of superfluid and superconducting matter. These currents generate and sustain the magnetic field, twisting it tighter over time until something gives. When it does, the resulting flare can sweep across the cosmos in less than a second, carrying enough energy to sterilize planets if they were unlucky enough to orbit nearby. Even in their quiet phases, magnetars are never truly still. Their fields decay slowly, releasing energy as they age. Over tens of thousands of years, they cool, their magnetic intensity weakening. Eventually, they fade into ordinary neutron stars, their fury spent, their brilliance gone. But for those brief cosmic moments when they are active, they are the most powerful magnets the universe has ever produced. Short-lived yet unforgettable, like lightning storms across eternity. What makes magnetars so mesmerizing is not just their violence, but their contradiction. They are both tiny and immense, dead and alive, silent and screaming. They do not emit light continuously like ordinary stars, yet when they do, they rival galaxies. They represent nature's ability to condense energy, to trap unimaginable forces inside something the size of a small city, and to unleash them in blinding flashes that can be seen across cosmic distances. Magnetars challenge the limits of physics itself. Under such extreme magnetic pressures, the laws governing atoms and particles behave differently. The vacuum of space near them may become polarized, filled with ghostly particles flickering in and out of existence. Even the direction of time and the speed of light can appear altered. They are windows into realms where human understanding begins to bend, where equations break down and only raw phenomena remain. Observing a magnetar is difficult. Most of the time, they are dormant, hiding behind veils of dust and gas. Only when they erupt do we see them, sudden flashes of high-energy light followed by faint X-ray glows that fade over weeks. Each time we detect one, we learn a little more about the universe's extremes. Their rarity makes them precious. Every observation is like catching a lightning bolt in a bottle. They reveal the truth of what stars can become when pushed to their most violent form. Some magnetars exist within remnants of their original supernovae, vast clouds of gas still glowing from the explosion that gave them birth. Within these glowing shells, the magnetar's field continues to sculpt the material, shaping filaments and waves that ripple outward like echoes. It is as if the star continues to paint even after its death, its magnetic hand stretching across light years to carve beauty from chaos. These nebulae are haunted places, glowing softly with the memories of violence. Occasionally, a magnetar's magnetic field interacts with surrounding plasma, creating radio emissions that pulse in rhythmic bursts. These are known as fast radio bursts, mysterious, millisecond flashes of radio energy that appear suddenly and vanish just as quickly. For years, their origin was unknown, but now we know that at least some come from magnetars. It is astonishing to think that a single twist of a magnetic field on a star thousands of light-years away can create a signal powerful enough to reach our telescopes. To a distant observer, a magnetar's flare might look like a brief flicker, a blink of light swallowed by darkness. But hidden in that flicker is an entire story, a crust cracking, magnetic lines snapping, and matter screaming into space. The energy travels for centuries through the void before it ever meets human eyes. And when it finally does, it tells us that somewhere out there, a dead star still remembers the violence of its birth. These stars are rare jewels of the cosmos. Perhaps only one in every 1,000 neutron stars becomes a magnetar, and of those, only a handful are ever caught in the act of flaring. Yet their impact on astrophysics is immense. By studying them, scientists have begun to understand how magnetic fields shape the universe, how they influence galaxy formation, star evolution, and even the mysterious behavior of dark matter. Magnetars, in their fury, teach us about the calm fabric of everything. A magnetar's lifetime is short, a few tens of thousands of years, but its influence can last much longer. The heavy elements formed in its explosion may become part of new planets. The energy it releases may trigger the formation of new stars nearby. Even after its light fades, it leaves a fingerprint on the structure of its galaxy. Death, in the universe, is never an end, it is a transformation, and magnetars are among the most dramatic examples of that truth. In the regions near the galactic center, where stars are born and die more frequently, magnetars may be more common. One such object was discovered near our own galaxy's central black hole, its radio pulses whispering through clouds of dust. It is astonishing to realize that in a place so chaotic, a single spinning remnant can still maintain its rhythm. The magnetar's presence there suggests that even in the most turbulent corners of the cosmos, order can survive in the form of rotation and magnetism. If you could somehow approach a magnetar safely, though no technology could allow it, you would see nothing unusual at first. Just a faint, dark sphere in the void. But as you drew nearer, the invisible hand of its magnetism would begin to shape the space around you. Atoms would stretch, electrons spiral, and light itself would shimmer like ripples on water. The emptiness around the star would feel alive, charged with invisible fire. It is power without color, presence without touch. The magnetic field lines that wrap a magnetar are vast and tangled, looping far into space before curling back. They twist, reconnect, and snap in sudden bursts, releasing radiation that races outward like the breath of a sleeping dragon. These outbursts remind us that the universe is not quiet, that even its deadest corners pulse with unpredictable life. In those brief flashes, we glimpse the hidden restlessness that drives creation itself. As centuries pass, the magnetar cools and its field weakens. It becomes less violent, its storms fewer and its bursts dimmer. Eventually, it will settle into the slow rhythm of a neutron star, no longer magnetic enough to tear the fabric of reality. But its past remains written in the radiation it left behind, in the waves it sent through space, in the elements forged by its birth. The monster sleeps, but its influence lingers, soft, persistent, eternal. The story of magnetars is the story of intensity, of the universe pushing itself to its absolute limits. They show us how much power can exist in something so small, how beauty and destruction can coexist in a single heartbeat of cosmic time. They remind us that the quiet night sky hides forces beyond imagination, that even the faintest flicker might come from a storm fierce enough to reshape worlds. In their silence and fury, magnetars stand as proof that the universe is both artist and engineer, crafting wonders that no human mind could ever fully comprehend. Binary predators, the Black Widow and other star-eating pairs. In the dark stretches of space, not all stars live alone. Some are locked in pairs, orbiting each other like dancers bound by invisible chains. But in certain cases, one partner becomes the hunter, a pulsar or neutron star feeding on the life of its companion. These are the Black Widow binaries, named after the spider that consumes its mate. In these systems, a once normal star is slowly devoured, its matter stripped away by the relentless radiation and gravity of its monstrous partner until almost nothing remains. The story begins with a supernova. A massive star explodes, leaving behind a neutron star or pulsar, a compact remnant spinning rapidly, throwing out powerful radiation and stellar wind. If another star happens to orbit close by, it finds itself trapped in a deadly relationship. The pulsar's magnetic fury bombards its companion with streams of charged particles, heating it, stripping it, reshaping it. The smaller star begins to shrink, its outer layers peeled off in a slow, eternal eclipse of light and life. Astronomers first discovered these strange couples through their rhythmic pulses. They noticed that certain pulsars had tiny, regular wobbles, signs of a gravitational partner orbiting nearby. But when they searched for that companion, they found only faint, fading traces. The partner star was not gone, not yet, but it was being consumed, whittled down by the predator's hunger. What remained was a ghostly ember, a fraction of its former self, clinging desperately to existence as it circled a monster that would not let it go. The Black Widow pulsar PSRB 1957+20 is one of the most famous examples. It spins hundreds of times per second, blasting its companion with winds moving at nearly the speed of light. Those winds carve away the smaller star's surface, turning it into a comet-like shape trailing plasma. Over millions of years, the pulsar will strip its partner down to nothing but a dense, lifeless core. It is a slow murder on a cosmic scale, quiet, cold, and inevitable. Some of these predator pairs are even stranger. In certain systems, the pulsar's companion is not a full star but a planet-sized remnant, all that's left after eons of erosion. These companions are so light that they barely qualify as celestial bodies, yet they still orbit faithfully, doomed to lose what little mass remains. Eventually, they may vanish entirely, leaving behind a solitary pulsar spinning alone, victorious, but forever haunted by the ghost of its lost companion. Astronomers call these pairs spider pulsars, dividing them into two families, black widows and redbacks. In the redback systems, the companion star is still large enough to fight back. It swells, throws off material, and sometimes pushes against the pulsar's wind, creating flickering arcs of radiation between them. The relationship is volatile, unstable, sometimes the pulsar dominates, sometimes the companion flares in retaliation. It's a cosmic tug-of-war between destruction and survival. The radiation from these pairs can be extreme. The side of the companion facing the pulsar glows fiercely, heated to thousands of degrees by constant bombardment, while the opposite side remains cold and dark. This creates a bizarre, half-lit world, one hemisphere forever burning, the other frozen. To an observer in orbit, it would appear as a star that breathes light, brightening and dimming with every rotation. These cycles are not gentle, they are the rhythm of a dying star. Black Widow pulsars are not content with just eating, they reshape their victims. The intense gravity can distort the companion, pulling it into a teardrop shape, and the outflow of matter forms streams of plasma between them. In some systems, this material gathers into an accretion disk around the pulsar, glowing with high-energy light as it spirals inward. The disk hums with X-rays, a whisper of the violence unfolding in silence. Even in destruction, beauty persists. The name Black Widow is not mere metaphor, it is nature repeating itself across scales. Just as the spider's venom slowly paralyzes and dissolves its prey, the pulsar's radiation weakens and consumes its companion atom by atom. It is a relationship both intimate and fatal, bound by gravity's grip and time's patience. The smaller star cannot escape, its orbit is its prison, and its predator its fate. Over time, as the companion loses mass, the orbit changes. The two bodies move closer, locked tighter in their embrace. The pulsar spins faster, feeding off the infalling matter like a whirlpool gaining strength. It can reach incredible speeds, thousands of revolutions per second, becoming what astronomers call a millisecond pulsar. These ultrafast rotators are powered by the very life they consume, their hunger turned into momentum. But even monsters can grow weary. After consuming their companions, Black Widow pulsars eventually exhaust their fuel. Their winds weaken, their light fades, and the silence returns. What remains is a lonely, rapidly spinning relic surrounded by the invisible ashes of its victim. To the universe, it's just another point of light. To us, it's a reminder that even stars can betray, that creation and destruction are entwined in the same cosmic dance. Some Black Widow systems defy explanation. There are triples, where a pulsar feeds on one companion while another orbits from afar, untouched. In others, the pulsar's rotation seems to speed up and slow down unpredictably, as if the dying companion's last outbursts still influence it. Each system tells a different story of dependency and decay, of balance tipping toward inevitable collapse. In the cold theater of space, these are dramas without witnesses, tragedies without sound. The radiation storms that pour from these pairs travel light-years away, brushing past other stars, carrying signatures of their torment. When we detect them on Earth, They arrive as faint flickers in radio waves or bursts of X-rays. Yet each pulse carries the fingerprint of destruction, the encoded story of a small star's death. To listen to them is to eavesdrop on a love story turned cannibalistic, a duet where one voice drowns the other in light. Some scientists speculate that black widow pulsars could eventually create strange remnants, ultralight companions composed mostly of carbon or degenerate matter. In theory, what's left could become something like a black diamond, a crystal of stellar remains orbiting a dead sun. It's a haunting image, beauty born from annihilation, glittering quietly in the dark, its existence proof of violence long past. The pulsar's spin is key to its appetite. As it rotates, it generates magnetic fields that accelerate charged particles, creating winds that sweep across space. The faster it spins, the more energy it releases, and the quicker it erodes its companion. This feedback loop can last millions of years, until the balance finally breaks and the smaller star is erased completely. The predator is both powered and imprisoned by its hunger. Not all binary predators end in victory. Some pairs spiral inward too far, merging into a single object, a neutron star reborn or, in extreme cases, a black hole. When this happens, the energy released can rival a supernova. The merger sends gravitational waves through the fabric of space, ripples that we can now detect with precision instruments. Each detected wave is a cosmic death cry, the last heartbeat of two doomed lovers fusing into one. In regions dense with stars, such as globular clusters, binary predators are more common. There, gravitational encounters frequently create new pairs, old pulsars capturing fresh companions, beginning the cycle anew. It's a quiet ecosystem of predators and prey, forming and dissolving over eons. Even in the stillness of the cosmos, life and death repeat endlessly, guided only by gravity's hand and time's indifferent gaze. The light curves of these systems, the way their brightness changes, tell astronomers everything. When the pulsar's radiation hits its companion, it glows. When it hides behind the pulsar, the light dims. These variations reveal the size, shape, and suffering of the smaller star. Each fluctuation is a heartbeat of the doomed, a rhythmic proof of destruction disguised as beauty. To imagine standing near one of these pairs is to imagine madness. The radiation alone would vaporize anything nearby. Space itself would seem to shimmer with invisible fire, the pulsar's beam sweeping like a blade through the darkness. You'd see the smaller star, distorted, trembling, bleeding streams of gas toward its companion, circling ever faster as it loses its fight. And around them, the night would glow faintly, illuminated by their ongoing war. Even in their violence, binary predators are essential to cosmic evolution. They recycle matter, enrich interstellar space, and forge millisecond pulsars that help us study gravity and time. They remind us that not all destruction is loss, sometimes it is transformation. The universe thrives on such exchanges, turning death into discovery, decay into light. In the end, when the feeding stops and the stars grow quiet, what remains is a strange peace. The pulsar spins on, cold and perfect, while the last traces of its companion fade into the void. Around them, the universe continues its endless hum, unaware of the tragedy that just unfolded. The Black Widow rests, her hunger momentarily sated, her story written in radiation and silence. And in that silence, the cosmos exhales, indifferent, eternal, and utterly beautiful. Stellar black holes, collapsed stars with a one-way skin. They are the heavy hearts left behind after the deaths of giant suns, places where gravity grows so strong that even light cannot escape. When a massive star burns through its fuel, its core collapses inward under its own immense weight. The matter inside is crushed into a singularity, a point of infinite density, surrounded by an invisible boundary called the event horizon. This horizon is the one-way skin of the universe, a border beyond which nothing returns. Not light, not time, not even the memory of what falls inside. From the outside, a stellar black hole gives nothing away. It has no surface, no color, no texture, only gravity. Yet it can be detected by what it does to its surroundings. When gas orbits too close, it spirals inward, heating up and glowing in X-rays before vanishing into darkness. This brilliant edge, this moment of final light, is all we ever see. The rest lies hidden, sealed away by physics itself. In this way, black holes are both visible and unseen, bright in their devouring, silent in their truth. The event horizon marks the ultimate limit. It is not a physical wall, but a threshold, the point where escape velocity equals the speed of light. Once crossed, space and time change roles, falling inward becomes inevitable, as if the universe itself were flowing into a drain. Nothing inside can send a message back. For any object that falls through, time slows from an outside perspective, freezing it forever at the edge, while for the falling object, the plunge feels swift, unstoppable, and strangely calm. Stellar black holes typically form from stars more than 20 times the mass of our Sun. When such a star runs out of nuclear fuel, its outward pressure fades, and gravity takes over. The outer layers explode outward in a supernova, while the core collapses inward at nearly the speed of light. The atoms are crushed beyond recognition, the space between particles eliminated. The result is a gravitational well so deep that not even photons, the fastest messengers in existence, can climb free. Though they are born from destruction, black holes bring order to chaos. Their gravity shapes galaxies, influences star formation, and stabilizes the orbits of entire systems. They are not just cosmic monsters, they are architects, sculpting the grand structure of the universe. Each one, silent and invisible, becomes a kind of anchor, a point where the laws of nature meet their limits, where equations break into mystery. The space around a black hole is not empty. It swirls with plasma, gas, and radiation, all pulled into furious motion by gravity's irresistible grip. This material forms an accretion disk, a glowing whirlpool of matter orbiting at near-light speed. The friction and compression heat it to millions of degrees, releasing powerful X-rays that telescopes can detect across light-years. The disk is a graveyard and a furnace, burning with the light of things that will never return. The energy released by this infalling matter can outshine entire galaxies. Jets of radiation and particles can shoot from the black hole's poles, piercing interstellar space with streams that extend for light-years. These jets are formed not from what escapes the black hole, but from the twisted magnetic fields at its edge, the last desperate expressions of matter before it crosses the point of no return. Each jet is a statement of power, a flare from the edge of eternity. For the companion stars that orbit a black hole, existence is perilous. In binary systems, the black hole feeds on its partner, pulling gas and plasma from its surface. This material spirals inward, forming the accretion disk and emitting deadly radiation. Yet, from afar, such systems can appear almost peaceful, a steady flicker of X-rays marking the rhythm of cosmic hunger. These feeding pairs are how we first learned to recognize stellar black holes, through their appetite. The first confirmed black hole, Cygnus X1, revealed itself in just this way. A massive blue star was seen orbiting an unseen partner, one that emitted intense X-rays but no visible light. The motion of the visible star betrayed the mass of the invisible one, too great to be a neutron star, too small to be a galaxy. It could be only one thing, a black hole. That discovery changed our understanding of death among stars, proving that even in the silence of the void, something still consumes. To fall toward a black hole is to fall toward the end of space as we know it. Near the horizon, gravity stretches and squeezes objects, a process scientists call spaghettification. The difference in gravity between your head and feet becomes enormous. Your body would be pulled apart, atom by atom. But the paradox is that from your own point of view, nothing feels unusual. You would pass the horizon without noticing, your perception of time and distance dissolving into the black. Inside, our theories fail. Einstein's equations describe the curvature of spacetime but cannot handle the infinite density of a singularity. Quantum mechanics, too, breaks down, leaving us without a unified picture. Somewhere inside a black hole lies a truth we cannot yet reach, a key to uniting gravity and quantum theory. It is as if the universe hid its most profound secret behind a veil of darkness, daring us to approach but never allowing us to see. The boundary of the event horizon also behaves strangely. It is not static, it vibrates, flexes, and responds to changes in mass and energy. When a black hole consumes matter, the horizon grows. When it loses energy through radiation, it shrinks. Stephen Hawking's groundbreaking work revealed that black holes are not entirely black, they emit faint radiation due to quantum effects at the edge, meaning they can, in theory, evaporate over unimaginable spans of time. This so-called Hawking radiation is incredibly weak for stellar black holes, almost impossible to detect, yet it carries profound implications. It suggests that black holes are not eternal, that even the universe's darkest prisons may someday vanish, leaving behind only faint whispers of energy. The ultimate fate of this radiation, and the information carried within, remains one of the greatest puzzles in physics. Does the black hole truly erase all that falls inside, or does some record persist in the light that escapes? To picture a black hole visually, one must think of warped light and bent reality. The immense gravity bends space so completely that light from behind it curves around, creating a glowing ring, the photon sphere, while the center remains utterly dark. This eerie halo is what was captured by the Event Horizon Telescope in 2019, giving humanity its first direct glimpse of a black hole's silhouette. That image was not a photograph of the hole itself, but of the light struggling to escape its edge. Around stellar black holes, time flows differently. For an outside observer, a falling object appears to slow endlessly as it nears the event horizon, its image fading and redshifting until it disappears. To the falling object, however, the journey continues smoothly, no pause, no resistance. It experiences time normally as the universe races forward outside. This duality, two realities coexisting, is what makes black holes so haunting. They distort not only space, but perception itself. Some stellar black holes drift alone, wandering the galaxy after their formation. These are the quiet predators, invisible except for the faint tug they exert on nearby stars or gas clouds. Occasionally, they may pass through a dense region, awakening briefly as they accrete matter and flare with X-rays. Then they vanish again, leaving only a ripple in space-time. The Milky Way may contain hundreds of millions of these dark travelers, unseen but always present. When two stellar black holes find each other, their fates intertwine. They orbit for eons, spiraling closer as they lose energy through gravitational waves. When they finally collide, the merger sends ripples through the fabric of space itself, waves we can now detect with instruments like LIGO and Virgo. Each detection is a whisper from billions of light-years away, proof that even darkness has a voice, and that time itself can be made to sing. These mergers create larger black holes, growing the cosmic population step by step. Over billions of years, such mergers may give rise to intermediate or even supermassive black holes, the titans that sit in the centers of galaxies. Thus, from small, stellar deaths come the largest engines in the cosmos. The story of every galaxy begins with the fall of a single star, a quiet collapse that becomes the seed of a celestial empire. To stand near a stellar black hole, if such a thing were possible, would be to feel reality stretch thin. The stars behind it would appear distorted, curved into rings and arcs. The light from distant galaxies would whirl and smear, pulled into an endless spiral. Time would feel sluggish, your heartbeat slow, your voice trapped before it could reach your ears. Then, silence, pure, infinite silence, the kind that no sound could disturb. And yet, in their silence, black holes speak volumes. They tell us that the universe is not infinite in kindness or chaos, but balanced, that everything which exists must someday return to its simplest form. Matter becomes energy, energy becomes curvature, and curvature collapses into darkness. Even there, the cycle continues, waiting for the moment when the black hole will fade and the light will begin again. Death, in space, is never truly the end. Stellar black holes remind us of humility. They are proof that even the mightiest stars can collapse into near-nothingness, that beauty and brilliance can vanish behind a single boundary of gravity. Yet their existence also proves that the universe keeps no waste, that even destruction creates form, and silence creates structure. They are the heartbeats we cannot hear, the mirrors that reflect no light, the graves from which galaxies grow. And somewhere, among the drifting dark, they wait, quiet, eternal, and endlessly watching. Gamma-ray bursts, brief, blinding cosmic lances. They are the most luminous explosions in the universe, appearing without warning and fading within seconds or minutes. From billions of light-years away, These bursts release more energy in a moment than the Sun will emit over its entire 10 billion-year lifetime. Gamma-ray bursts, or GRBs, are fleeting flashes, yet their impact on astrophysics is immense, offering a glimpse into the life and death of massive stars, the collision of neutron stars, and the extremes of spacetime itself. GRBs fall into two main categories: long-duration and short-duration bursts. Long bursts, lasting more than 2 seconds, usually signal the death of a massive star. When such a star exhausts its nuclear fuel, its core collapses into a black hole, and the outer layers are ejected in a colossal explosion. This creates a narrow, high-energy jet that pierces through the star and shoots across the cosmos. Short bursts, under 2 seconds, often originate from collisions between neutron stars, a violent merger that also produces gravitational waves detectable across galaxies. Imagine a narrow beam of radiation, moving close to the speed of light, sweeping across the universe. These beams carry energy so concentrated that, if one were aimed at Earth from nearby, it could strip away the atmosphere and sterilize the planet in seconds. Fortunately, such events are extraordinarily rare in our galaxy. Yet billions of light-years away, GRBs remind us that the universe is capable of both sudden creation and sudden destruction, pushing physics to its limits in mere instants. The first GRBs were discovered in the late 1960s by satellites designed to monitor nuclear explosions on Earth. Scientists were baffled as flashes of gamma rays appeared, seemingly originating from deep space. At first, their origin was a mystery, prompting wild theories. Some even considered extraterrestrial civilizations. Decades later, with the advent of space-based telescopes sensitive to high-energy light, astronomers began to locate GRBs in distant galaxies, confirming that these were natural, astrophysical phenomena of incredible power. The host galaxies of GRBs are often small, young, and star-forming. They are crowded nurseries where massive stars live fast and die young. In these regions, long GRBs are most likely to occur, marking the spectacular deaths of stars that burn brightly and collapse violently. The explosions are not isotropic. Their energy is concentrated in narrow jets, which means that only observers within the path of the beam see the full brightness. For others, the event is nearly invisible, a reminder that perspective governs our understanding of the cosmos. When a GRB occurs, it produces not only gamma rays but also afterglows across the electromagnetic spectrum: X-rays, ultraviolet, optical, and radio waves. These afterglows fade slowly over days or weeks, providing astronomers with valuable information about the burst's environment and the processes powering it. The afterglow can illuminate the interstellar medium, revealing the density, composition, and magnetic fields of the surrounding space. In this way, GRBs serve as cosmic lighthouses, probing regions that would otherwise remain hidden. The jets themselves are fascinating phenomena. Focused, narrow, and incredibly energetic, they challenge our understanding of relativistic physics. The material within moves at velocities approaching light speed, and relativistic effects amplify the energy and brightness seen by observers aligned with the jet. Magnetic fields twist and shape the outflow, creating shocks that accelerate particles and generate the gamma rays we detect. The jets are natural accelerators, producing energies far beyond what human-made devices could ever achieve. Neutron star mergers, responsible for short GRBs, produce bursts that are no less extreme. When two neutron stars spiral into each other, they release gravitational waves and gamma rays simultaneously. The event is brief, but the energy is concentrated into an astonishingly small region of space. The resulting jet punches through the debris, emitting a brief flash of gamma rays detectable across the universe. These mergers are also sites of heavy element formation, seeding galaxies with gold, platinum, and other precious materials. GRBs are not just distant fireworks, they influence their surroundings. The intense radiation can ionize nearby gas, trigger star formation, or even blow apart clouds of dust and plasma. Their energy can sculpt the interstellar medium on scales of hundreds of light-years, leaving a lasting mark on the galaxy. In this sense, GRBs are both destructive and creative, shaping the evolution of galaxies even as they mark the violent deaths of individual stars. Observing GRBs requires rapid response. The gamma ray flash itself may last seconds, but afterglows persist long enough to study. Space telescopes equipped with rapid alert systems, like NASA's Swift Observatory, detect bursts and immediately relay coordinates to ground-based telescopes. Astronomers around the world then aim optical, radio, and X-ray instruments at the location, capturing fading light that can reveal the redshift, distance, and host galaxy properties. Coordination is key, as every minute counts before the afterglow dims. GRBs also test our understanding of physics under extreme conditions. The jets are ultra-relativistic, moving at nearly the speed of light, compressing time and space for particles inside. Shockwaves accelerate electrons to energies millions of times higher than in a laboratory. Magnetic fields twist, reconnect, and create turbulence. Studying these bursts pushes the boundaries of particle physics, plasma physics, and high-energy astrophysics, revealing how the universe behaves when energy is concentrated in an extraordinary way. In some cases, GRBs have been associated with supernovae, linking long bursts to the collapse of massive stars. The supernova explosion forms the black hole, while the GRB arises from a focused jet along the rotational axis. Observers aligned with this axis witness the full intensity, while those at other angles see only the supernova. This alignment effect explains why not every massive star collapse produces a detectable GRB, highlighting the role of geometry and chance in our observation of the cosmos. Gamma-ray bursts are cosmological probes as well. Because they are so luminous, they can be seen across vast distances, even from the earliest epochs of the universe. Detecting a GRB from a galaxy billions of light-years away allows astronomers to study conditions in the early universe, including star formation rates, metallicity, and the distribution of matter. In this way, GRBs serve as cosmic beacons, illuminating the history of the universe itself. Some GRBs are accompanied by polarization in their light, indicating the presence of ordered magnetic fields in the jet. The degree and orientation of polarization provide clues about the jet structure, its geometry, and the mechanisms accelerating particles. Polarimetric studies are still in their infancy, but they reveal that GRB jets are not chaotic explosions. They are structured, coherent, and shaped by fundamental forces acting on scales that challenge human intuition. The duration and variability of GRBs also contain vital clues. Long bursts often exhibit multiple peaks and substructure, hinting at the dynamics of the collapsing star and the formation of the jet. Short bursts, while briefer, may show complex pulses reflecting the violent merger of neutron stars and the subsequent formation of a black hole. By analyzing light curves, astronomers can infer the physical processes at play, from core collapse to relativistic shocks to magnetic reconnect ion. While rare locally, GRBs are common on cosmological scales. Every day, bursts occur somewhere in the observable universe, yet only a tiny fraction point toward Earth. This rarity has allowed life to flourish on our planet, as a nearby burst could have catastrophic consequences, stripping the atmosphere and irradiating the surface. The existence of GRBs serves as a reminder of the fragility of habitability in a universe full of sudden, blinding energy releases. The first afterglow observations in the late 1990s revolutionized our understanding. GRB 970228 revealed fading optical emission, confirming the extragalactic origin of these bursts. Subsequent observations showed redshifts indicating distances of billions of light-years, cementing the fact that GRBs are truly cosmic-scale events. These discoveries also linked bursts to star-forming regions, confirming theories that massive stars and neutron star mergers are the progenitors. The light from a GRB carries signatures of its journey. Absorption lines reveal the material it passed through, from gas in the host galaxy to intergalactic hydrogen clouds. Each burst is a probe, mapping matter across billions of light-years. In this way, GRBs serve as natural spectrographs, offering insights into cosmic chemistry, galaxy evolution, and the large-scale structure of the universe. They are messengers, traveling across space to tell stories written in light. Some GRBs are so powerful that their afterglows persist for weeks or even months. Observing these long-lasting emissions allows astronomers to study the environment around the burst in detail, including magnetic fields, density variations, and relativistic shocks. These studies reveal that GRBs are not isolated explosions but interact dynamically with their surroundings, influencing star formation, gas distribution, and even the evolution of their host galaxies. The theoretical modeling of GRBs is a complex challenge. Simulations must account for relativistic fluid dynamics, magnetic fields, nuclear reactions, and radiation transport, all in 3 dimensions. Tiny changes in initial conditions can drastically affect the observed burst. Yet these models have begun to reproduce many features seen in real GRBs, confirming our understanding of relativistic jets, progenitor collapse, and particle acceleration. They are laboratories for testing the limits of physics in ways impossible on Earth. Gamma-ray bursts remind us that the universe is violent, transient, and astonishingly energetic. In mere seconds, a burst can release more energy than the Sun in its entire lifetime, illuminating galaxies billions of light-years away. They are cosmic lances, brief, blinding, and unforgettable, demonstrating that even in the vast calm of space, cataclysm and brilliance coexist. They teach us about birth, death, and the extremes of matter and energy, leaving humanity in awe of the fleeting yet monumental dramas of the cosmos. Fast radio bursts, tiny, uncanny pulses from the deep. FRBs are sudden flashes of radio waves that last mere milliseconds, yet their energy rivals what the Sun emits in an entire day. First discovered in 2007, these brief signals puzzled astronomers. They appeared without warning, from far beyond our galaxy, and carried no obvious source. Each burst is like a cosmic Morse code, a brief whisper from the universe, hinting at violent processes occurring in distant corners of space that we are only beginning to understand. The origins of FRBs remain one of modern astronomy's greatest mysteries. Some bursts repeat, while others are one-off events, suggesting multiple mechanisms at work. Theories range from magnetars, highly magnetic neutron stars, to the mergers of compact objects, to exotic possibilities like collapsing black holes. Their extreme brightness and brief duration indicate they originate from compact, highly energetic sources, where extreme physics can twist and concentrate energy into a millisecond pulse capable of traversing billions of light-years. Despite their fleeting nature, FRBs provide a unique window into the cosmos. The radio waves interact with the interstellar and intergalactic medium, dispersing and spreading in a predictable manner. By analyzing this dispersion, astronomers can estimate the amount of matter the waves passed through, effectively using FRBs as probes to map the distribution of gas and plasma in the universe. They become tools for studying structures otherwise invisible, revealing the hidden scaffolding of galaxies and clusters. Some FRBs repeat with regular or semi-regular intervals, suggesting periodic behavior. The repeating source FRB 180916, for instance, exhibits a 16.35-day cycle of activity, which hints at orbital motion or precession effects. These repeating bursts challenge theories that FRBs arise solely from cataclysmic events and point instead toward dynamic, energetic systems that can survive multiple eruptions, such as magnetars with shifting magnetic fields or binary systems in which interactions trigger bursts. FRBs are astonishingly bright given their small size and brief duration. In a fraction of a second, the energy released in a burst can equal the output of hundreds of millions of suns over the same period. Such concentration suggests the source is extremely compact, likely no larger than a city or a neutron star, and capable of generating immense electromagnetic forces. Their brevity also implies the source operates on tiny spatial and temporal scales, forcing astronomers to confront extreme regimes of physics that cannot be replicated in laboratories. Observing FRBs requires highly sensitive radio telescopes and fast detection methods. Instruments like CHIME in Canada and FAST in China have revolutionized the field, capturing thousands of bursts and enabling statistical studies of their properties. CHIME, with its wide field of view, detects dozens of FRBs per day, including many repeaters, while FAST's unparalleled sensitivity allows precise localization and identification of host galaxies. Together, they are revealing patterns and structures that hint at the origins of these enigmatic pulses. The host galaxies of FRBs are diverse. Some originate in star-forming dwarf galaxies, while others come from massive spiral galaxies. Their locations within these galaxies vary too, sometimes near the core, sometimes in spiral arms, suggesting that multiple progenitor types may produce FRBs. Studying the local environment density, magnetic field strength, and nearby stellar populations provides vital clues. These bursts are not random flashes, they are rooted in specific, energetic cosmic habitats. The polarization of FRB signals is another key feature. Many bursts show strong linear or circular polarization, indicating that their waves have passed through highly magnetized environments. This suggests that the sources are immersed in intense magnetic fields, consistent with magnetars or compact binary systems. Polarization measurements allow astronomers to probe the magnetic conditions near the source and along the line of sight, adding another layer to our understanding of cosmic environments far beyond the reach of optical telescopes. Dispersion measures of FRBs reveal the total column of free electrons along their path. By comparing the observed dispersion with models of the Milky Way's electron content, astronomers infer the distance to the source. Many FRBs originate billions of light-years away, making them among the most distant signals detectable from individual astrophysical events. Each burst is a cosmic telegram sent across time and space, carrying information about the intergalactic medium and the large-scale structure of the universe. FRBs have inspired exotic hypotheses. While most are now attributed to natural astrophysical processes, some researchers have speculated about artificial origins, beams or signals from extraterrestrial civilizations. While such ideas remain speculative, they underscore the mystery and novelty of FRBs. Their extreme properties, brevity, and intensity make them unlike any other known astrophysical phenomenon, leaving room for creative and rigorous exploration alike. The brightest FRBs can momentarily outshine all the radio emission of their host galaxy. Such bursts reveal the enormous efficiency with which energy is converted into radio waves. Unlike supernovae or gamma-ray bursts, which release energy across multiple wavelengths, FRBs concentrate their output almost entirely in radio frequencies, suggesting a mechanism that channels energy into coherent radiation rather than thermal emission. This is a critical clue about their underlying physics. FRBs can also produce afterglows at other wavelengths, though these are rare and faint. X-ray or optical counterparts provide additional data, allowing astronomers to connect the radio pulse to energetic events in the source's environment. These multi-wavelength observations are essential for constraining progenitor models, revealing whether the burst is associated with a supernova, magnetoflare, or another transient event. Each additional wavelength is a piece of the puzzle in understanding these cosmic flashes. Timing of FRBs is extraordinary. With millisecond durations, their detection pushes the limits of radio instrumentation. The signal's rapid rise and fall mean that even tiny delays in observation can result in missed events. Advanced digital processing, real-time analysis, and rapid coordination between telescopes are required to catch and study FRBs effectively. Their ephemeral nature challenges astronomers to think and respond at speeds that match the cosmic phenomena themselves. FRBs are not only useful for studying their sources but also for probing fundamental physics. The propagation of radio waves through space tests theories of dispersion, plasma physics, and even aspects of relativity. Variations in arrival times across frequencies reveal the nature of intervening matter. In essence, FRBs are tiny experiments conducted by the universe itself, using distant cosmic laboratories inaccessible to Earthbound scientists. Some repeating FRBs display complex substructure, multiple peaks within a single burst or variations in frequency and intensity. This suggests that the emission region is dynamic and turbulent, possibly influenced by magnetospheres, accretion disks, or binary interactions. Understanding these fine details requires high-resolution data and sophisticated modeling, revealing that even the briefest bursts encode rich information about their origin. FRBs challenge our notions of scale. A millisecond flash can carry as much energy as a large-scale supernova emits in days, condensed into a tiny volume. This incredible concentration implies that the source is not only energetic but also extremely compact. Processes such as magneto-magnetic reconnect ion, relativistic shocks, or neutron star collisions are among the few mechanisms capable of producing such bursts, making FRBs windows into physics at the edge of possibility. Some FRBs repeat with irregular patterns, defying predictions. The intervals between bursts can vary from seconds to years, suggesting complex triggering mechanisms. This unpredictability makes them difficult to study but also hints at rich underlying physics, possibly involving rotational or orbital dynamics, starquake events, or magnetic field instabilities. Each repeating source may have its own unique signature, a fingerprint of its cosmic life story. Localization of FRBs is now possible with interferometers and radio arrays. Pinpointing their host galaxies allows astronomers to connect bursts to specific environments, stellar populations, and cosmic history. Some localized FRBs are near star-forming regions, others in older, quiescent areas. The diversity of environments suggests that multiple progenitor pathways exist, making FRBs not a single type of event, but a phenomenon encompassing a spectrum of cosmic processes. The discovery rate of FRBs is accelerating. Early surveys detected just a handful, but modern wide-field telescopes now find dozens or hundreds per year. This growing sample allows statistical studies, revealing population trends, luminosity distributions, and correlations with galactic environments. Each detection refines our models, bringing us closer to understanding the conditions that produce these enigmatic flashes and the frequency with which they occur across the universe. FRBs have cosmological significance. Their dispersion measures allow for independent estimates of baryonic matter in the universe, helping to solve the mystery of the missing ordinary matter that eludes detection in galaxies and clusters. By mapping the dispersion of hundreds or thousands of FRBs, astronomers can construct a three-dimensional picture of matter distribution across cosmic scales, making these tiny pulses powerful tools for understanding the structure of the universe. Fast radio bursts are tiny, uncanny messengers from the cosmos. In milliseconds, they convey energy, structure, and mystery across billions of light-years. They challenge our understanding of physics, astrophysics, and the behavior of matter under extreme conditions. Each pulse is a whisper from the deep, a signal that the universe is far stranger and more dynamic than our daily experience suggests. FRBs remind us that even the briefest flashes can illuminate vast truths, and that the cosmos still holds secrets waiting to be decoded. Fast radio bursts, tiny, uncanny pulses from the deep. These fleeting flashes of radio waves last only milliseconds, yet their energy output is staggering, sometimes releasing as much energy in a single burst as the sun emits over an entire day. Discovered in 2007, FRBs first puzzled astronomers because they appeared randomly, with no apparent source within the Milky Way. Each pulse is a cryptic message from the universe, traveling billions of light-years, whispering secrets of violent astrophysical processes, extreme environments, and cosmic phenomena still largely unknown. FRBs are broadly categorized into repeating and non-repeating bursts. Repeating FRBs emit multiple pulses over time, sometimes in predictable cycles, while non-repeating bursts appear once and vanish. This division suggests multiple origins and mechanisms. Some bursts arise from magnetars, neutron stars with extremely strong magnetic fields, while others might result from collisions between compact objects, such as neutron stars or white dwarfs. The brevity and intensity of these pulses indicate extremely compact, highly energetic sources capable of producing rapid, coherent radio emission. The mechanism behind FRB emission remains an active field of research. In some models, magnetic reconnect ion events on magnetars trigger bursts of energy, sending jets of coherent radio waves into space. In others, the collision of two neutron stars produces a short, intense flash. Regardless of the origin, the bursts travel through vast stretches of intergalactic medium, interacting with plasma and cosmic magnetic fields along the way. This journey disperses and stretches the signal, allowing astronomers to measure the density and composition of matter between galaxies. Observationally, FRBs are detected using sensitive radio telescopes equipped with fast, wide-field receivers. Instruments like CHIME in Canada and FAST in China have dramatically increased the discovery rate, capturing hundreds of bursts and identifying repeating sources. CHIME, with its large field of view, detects dozens per day, while FAST's enormous collecting area allows precise localization. Each detection involves real-time data processing and rapid alert systems so that follow-up Observations across multiple wavelengths can study the host galaxy and immediate environment. The host galaxies of FRBs vary widely. Some originate in star-forming dwarf galaxies rich in young, massive stars, while others appear in larger spiral galaxies with older stellar populations. The locations within these galaxies differ as well, with bursts sometimes occurring near galactic centers and sometimes in the outskirts. These variations suggest multiple progenitor channels, meaning that FRBs are not a single type of astrophysical event but a diverse set of phenomena that produce similar observable radio flashes. FRBs provide unique probes of the universe. As the radio waves travel across intergalactic space, they interact with free electrons, resulting in dispersion, a frequency-dependent delay. By measuring this delay, astronomers can estimate the total electron content along the line of sight, giving insights into the distribution of matter between galaxies. FRBs thus act as cosmic lighthouses, mapping structures and densities in regions that are otherwise invisible, allowing researchers to study the large-scale structure of the universe. Repeating FRBs have revealed intriguing periodicity. For example, FRB 180916 exhibits a 16.35-day cycle of activity, suggesting the source is influenced by orbital motion or precession effects. This behavior indicates a stable, long-lived source rather than a single catastrophic event. Other repeaters, however, show irregular intervals, hinting at complex internal dynamics or interactions with a surrounding environment. These patterns provide clues about the astrophysical processes powering the bursts and the nature of their progenitors. Polarization measurements of FRBs reveal highly magnetized environments. Some bursts show strong linear or circular polarization, indicating the influence of intense magnetic fields near the source or along the line of sight. These observations are consistent with magnetars or neutron star binaries, where magnetic stresses can generate powerful, coherent radio emission. Polarization studies not only provide insight into the source but also allow astronomers to probe magnetic fields in intergalactic space, which are otherwise challenging to detect. The duration and structure of FRBs are remarkable. Bursts last milliseconds but can contain subpulses, frequency drifts, and complex fine structures. These features suggest that the emission region is turbulent and dynamic, influenced by extreme magnetic and relativistic effects. By analyzing these tiny variations, astronomers can infer details about the source's size, energy distribution, and local environment, providing indirect glimpses of phenomena occurring in regions far too small and distant to observe directly. Some FRBs are extraordinarily luminous. A single burst can outshine all the radio emission of its host galaxy for a brief moment, concentrating immense energy into a narrow beam. The efficiency of converting energy into coherent radio waves is astonishing, far exceeding the efficiency of typical astrophysical processes. Such extreme energy densities suggest that only compact, highly magnetized objects like neutron stars or magnetars are capable of producing these enigmatic flashes, making FRBs laboratories for high-energy physics under extreme conditions. The localization of FRBs has advanced rapidly. Using interferometry and rapid response arrays, astronomers can pinpoint bursts to their host galaxies with incredible precision. Some FRBs are associated with young, magnetar-rich regions, while others lie in older stellar populations. This diversity reinforces the idea that FRBs arise from multiple progenitor mechanisms. Precise localization also allows multi-wavelength follow-up, helping to connect the radio flash to potential X-ray, optical, or gamma-ray counterparts, shedding light on the physics of the source. FRBs are valuable tools for cosmology. Their dispersion measures trace the distribution of baryonic matter in the intergalactic medium, providing estimates for the elusive missing ordinary matter in the universe. By analyzing hundreds or thousands of FRBs, astronomers can construct three-dimensional maps of matter across cosmic scales. In this way, FRBs serve as natural probes, revealing the large-scale structure of the universe and offering insights into the evolution of galaxies, clusters, and the intergalactic medium over billions of years. The progenitor models for FRBs are diverse. Magnetars are prime candidates, as their magnetic fields can store and release tremendous energy in sudden flares. Other possibilities include neutron star mergers, collapsing black holes, or exotic phenomena involving cosmic strings or dark matter interactions. The repeating nature of some FRBs points toward stable, long-lived sources, while one-off bursts suggest cataclysmic events. Untangling these mechanisms requires detailed observations, modeling, and statistical studies. Across large populations of bursts, FRBs challenge our understanding of time and scale. Despite lasting only milliseconds, each burst travels billions of light-years, carrying information across vast cosmic distances. The speed, brevity, and intensity of these pulses force astronomers to consider physics in extreme environments, where energy is concentrated into tiny volumes, magnetic fields are intense, and relativistic effects dominate. FRBs are ephemeral yet cosmically significant, revealing processes that are as fleeting as they are powerful. Some FRBs are associated with persistent radio sources in their host galaxies. These sources may represent magnetar-wind nebulae, supernova remnants, or regions of intense star formation. The association suggests that certain FRBs occur in environments rich in energetic processes, where magnetic fields, particle acceleration, and plasma turbulence can contribute to burst generation. Studying these persistent sources alongside bursts helps constrain models of the emission mechanism, and the conditions required to produce FRBs. Multi-wavelength observations are key to understanding FRBs. While the bursts themselves are radio flashes, follow-up in optical, X-ray, and gamma-ray wavelengths can reveal associated phenomena, such as supernovae, magnetar flares, or transient nebulae. These observations are challenging due to the short duration of the bursts and the need for rapid response, but they are crucial for building a complete picture of the source and its environment. Each detection adds layers of detail to the puzzle of FRB origins. The repeating FRBs have revealed intricate patterns within bursts, including frequency-dependent structures and variations in intensity. These patterns suggest that the emission region is highly dynamic, with relativistic plasma flows, magnetic reconnect ion events, or shock interactions shaping the signal. Such detailed structures encode information about the extreme physics at the source, offering a rare glimpse into processes that are otherwise inaccessible to direct observation. FRBs also serve as laboratories for testing fundamental physics. By examining their propagation, scientists probe the nature of space, plasma physics, and even potential deviations from Einstein's theories of relativity. Tiny delays, frequency-dependent effects, and polarization measurements allow constraints on the intergalactic magnetic field, electron density, and potential exotic phenomena. FRBs are, thus, both astrophysical mysteries and practical tools for exploring the deep universe. Despite their mysterious nature, FRBs are becoming more predictable in terms of discovery. Modern radio surveys continuously scan the sky, uncovering hundreds of bursts annually. Large datasets allow astronomers to categorize bursts by energy, duration, repetition rate, and host environment, revealing trends that help refine theoretical models. With each new FRB, the universe delivers a brief, intense message, challenging our understanding while offering the promise of new discoveries. Fast radio bursts are cosmic enigmas, tiny, fleeting pulses carrying immense energy across billions of light-years. They illuminate their surroundings, map the universe, and probe the limits of physics in ways no other phenomenon can. Repeating and one-off bursts alike reveal the diversity of cosmic processes, from magnetar flares to neutron star mergers. FRBs are whispers from the depths of space, tiny yet powerful, brief yet infinitely informative, reminding us that even the briefest flashes can contain the secrets of the cosmos. These uncanny pulses, milliseconds long, challenge our perception of time and energy. They show that even in a universe that often appears calm and unchanging, sudden, violent processes are constantly occurring. Each FRB is a testament to the extremes of astrophysics, a reminder that the cosmos is energetic, unpredictable, and astonishingly creative. By studying these bursts, we learn not only about their immediate sources but also about the vast, invisible structures that fill the universe, connecting the infinitesimal and the infinite. FRBs inspire both curiosity and humility. Their brevity belies their significance, forcing astronomers to develop ever faster, more sensitive instruments and innovative methods of analysis. They demonstrate that even the tiniest pulses can illuminate vast cosmic truths, bridging the gap between human perception and the extreme scales of the universe. Each detection reinforces the idea that the universe communicates in subtle, fleeting messages, and that understanding these whispers is key to unlocking its deepest secrets. Ultimately, FRBs are cosmic signposts. They mark regions of intense magnetic, gravitational, and energetic activity, providing clues about the life and death of stars, the behavior of compact objects, and the distribution of matter in space. Though tiny and brief, each burst travels across billions of light-years, carrying information that transcends time and distance. Fast radio bursts remind us that the universe speaks in flashes and whispers, and that even the smallest signals can reveal monumental truths about the cosmos. The study of FRBs is accelerating, with new discoveries emerging almost daily. Each burst adds to a growing catalogue, offering statistical power to test theories and refine models. As more repeaters are identified, as more host galaxies are localized, and as multi-wavelength follow-ups improve, the enigma slowly yields its secrets. Yet the universe keeps its ultimate mysteries: why some sources repeat and others do not, how the energy is focused so efficiently, and what hidden physics underlies each pulse. Fast radio bursts are cosmic paradoxes, fleeting yet powerful, mysterious yet informative, simple in appearance but complex in origin. They illustrate the extremes of the universe, where milliseconds can carry unimaginable energy, and tiny sources can affect our understanding of cosmic structures. These uncanny pulses challenge us to rethink the nature of astrophysical phenomena, forcing humanity to look deeper, measure faster, and imagine more boldly the possibilities of the cosmos. In the end, FRBs are a reminder of the universe's rhythm, moments of silence punctuated by extraordinary events. Each millisecond pulse is a fleeting heartbeat from a distant, extreme environment, a testament to the violence, beauty, and creativity of cosmic processes. They teach us that even the smallest, briefest phenomena can hold profound significance, offering insight into the forces, structures, and mysteries of a universe far larger and stranger than our immediate experience.